Hi, I'm Mark Brooker, and today I wanted to talk about some of the work that we're doing around lightweight virtualization in AWS serverless, and some of that work that I think is going to interest the systems community. I'm a senior principal engineer at AWS, and I spend my time working on serverless and serverless databases. And this talk is mostly focused on AWS Lambda. This talk will be about 20 minutes long, and what I'm going to cover is what we're doing today, some of the opportunities that we see for the future of the virtualization area, some of the challenges that we see for the near future, and things that we're currently facing, and some new and exciting research directions. First, what are we doing? Most of this talk is going to be in context of Firecracker. Firecracker is a lightweight VMM optimized for serverless and container applications. We released Firecracker in 2018, and we've been using it in production in multiple areas of AWS. Mostly today, though, I'm going to be talking about it in context of AWS Lambda, where we are processing trillions of requests per month using Firecracker micro VMs. We're also investing in multiple areas. For example, the AWS Nitro system, which powers EC2, Rust VMM, which is a toolkit for building custom VMMs and hypervisors, and many others. This talk doesn't really cover any of those, and so my focus is on Firecracker and serverless and container applications. How are we using this in Lambda? Lambda, for those who don't know, is a serverless compute product. It's function-based. You give us a piece of code, and we will run that piece of code as an API or based on events or behind a load balancer and so on. Each function can be very small. 128 megabytes is the smallest size we support, up to quite big, so 3 gigabytes. And we run at Lambda at a very big and constantly growing scale, hundreds of thousands of concurrent workloads. Every single Lambda function gets, from the smallest ones to the biggest ones, runs on its own dedicated micro VMs. And in fact, every concurrent invocation of every Lambda function runs in its own dedicated micro VM. And so if you're running 100 concurrent Lambda functions, every one of those concurrents will get in its own Firecracker-powered, hardware-backed micro VM. This is using KVM under the covers on Linux, and this is all running on EC2 Metal instances. And so, we are creating and tearing down virtual machines at a very, very big scale. And so we care very deeply about the performance of these things, their startup costs, and so on. And we have hundreds of thousands of concurrent workloads running on Lambda, running on these micro VMs today in production, and have been doing that for quite some time. Like with all AWS services, our first priority is security and isolation. We care about compatibility. We want customers to be able to bring their existing code, their existing applications, the existing things that they've written, and bring them into the serverless compute environment, into AWS Lambda, without changing that code, without even, in some cases, having to recompile. And so what we want to do is provide an environment that is fully compatible at the source code level, at the API level, and at the ABI level with a lot of what customers are already familiar with. And then we also care deeply about performance. We don't want there to be compromises on performance by picking serverless compute. And so earlier this year, we published at NSDI our paper, Firecracker, Lightweight Virtualization for Serverless Applications. This paper that I wrote with a whole bunch of colleagues covers the design of Firecracker, the implementation of Firecracker, how we compare it to other solutions that go after similar problems in the serverless and container space, and it also covers exactly how it works in Lambda and some of the things that we've learned operationally by running this thing So do check that out if you want to get down into the details, and check out the source code of Firecracker and Rust VMM out on GitHub. Next, I want to talk a little bit about where we're going. Obviously, this is not a complete AWS roadmap of any kind. I just want to talk about some of the things that we're thinking about in the team, and especially ones that I think are going to be interesting to this community because of the system's implementation challenges behind them. One of them is relying more and more on VM snapshots and avoiding reinitialization of code. And I'm going to get into exactly what this means, but reinitialization of code for serverless and container workloads. And this is a latency optimization, it's a performance optimization. In some cases, it's a cost optimization. But it's a really important thing for optimizing serverless workloads. We're investing deeply in performance, network, block, and so on. Both density, because we need that great performance, but we need it on many hundreds to thousands of micro VMs on a single machine, and agility, being able to move those workloads in and out really quickly. And we're also continuing to invest in bringing virtualization and the stronger security boundary that brings to the wider container ecosystem and container community. So let's step a little bit into what the life cycle of a Lambda micro VM looks like. So first we boot up a kernel in the micro VM, and this is undifferentiated work. We do it many times the same way, and we use a little bit of pooling to completely hide this latency from customers. And then when a micro VM gets identified as the one that's going to run a function, we obviously need to download and bring the function code into that micro VM. That generally happens quite quickly because the code is fairly limited in size. But the next phase is where we add a lot of latency, and that is code initialization. And that's going to be things like loading binaries, Java class loading, jitting, running static code, running those startup codes and bootstraps and so on. And depending on what happens in that code, that can be anything from 100-ish milliseconds up to 60 seconds or even more, right? Especially Java code can do a lot of work at startup time in that static code, in frameworks and so on. And then once that's done, we can start giving invokes. And so we'll give many invokes for that same function to the same micro VM, each one with less than 10 milliseconds of overhead. And so our customers call the cases where they have to wait for this initialization cycle a cold start, and they call the cases where they don't have to wait for this initialization cycle a warm start. And we care very deeply about optimizing the performance of both of these modes, and have features like provision concurrency where customers can pre-provision a pool that we will keep cold started for them. But despite that, we would like this problem to go away. Unfortunately, we have relatively limited leverage because we don't own this code. Again, it's a function that our customers have written, they've brought to us, and we can provide all kinds of guidance and help and toolkits for optimizing that code, but we have fairly little control there. And so one of the things that we're trying to do with VM snapshots, and I'm not going to go into a lot of technical detail, but the basics here are we're going to take those create, we're going to take the download and the initialization step. And then once those are done, we're going to create a memory and CPU state and driver state snapshot of that micro VM. And this is very familiar kind of VM snapshotting step, full copy of the memory down onto, or sparse copy of the memory, I guess, down onto disk. Along with register state and the states of drivers and so on. And that captures everything and all that running code, the guest kernel, page caches and everything. So everything inside the guest memory. And then we can take that memory and we can make many clones of it. It's just a file on disk at this point. And so we can make as many copies of that as we would like. And then on the first warm start for a particular micro VM, instead of going through that boot download init, we can just restore a snapshot. And and snapshot restore can actually be extremely fast, single-digit milliseconds in some cases, especially because state is the state that really just needs to be there, the CPU state, and the driver state is very small. And memory state can come in, on demand as needed in the background. And so that means that we can be ready to invoke in a much shorter time without having to rerun that initialization code. And it also means that all of the stuff that is on the kind of blocking path, right, of invoking a function is things that are under our control. We can invest deeply in optimizing that restore path and therefore improve latency a great deal. And there's been some really interesting research work going on with similar ideas. Here are two papers I read recently on that topic. But there's a lot going on that's very interesting here. And I'm just super excited about the number of researchers who are looking at these kinds of problems and looking at solutions very, very creatively. So let's talk about some of the challenges of doing that. One of the challenges is with pseudo-random number generators. And that's because, a lot of pseudo-random number generators depend on some amount of user space state, right? They'll start up, they'll seed themselves from, from something like urandom or from a hardware random number generator, from RDRAND, and then they will keep state in memory and use one of the DRBG type algorithms to just create a kind of stream of PRNG state from that. And the challenge there is if you take that memory and you clone it, you end up with two PRNGs that have exactly the same state, right? And that means that they are going to, unless reseeded, they are going to create the same random numbers. That's kind of bad, but let's jump into one case where it is particularly bad, and that is in cryptography. So if we pick a cryptographic mode like AES-GCM, this is the Galois counter mode of AES. And we can go and look at what NIST says about the initialization vector. It's kind of the first, it's one of the inputs into the first step of GCM. And they say the probability that authenticated encryption function will ever be invoked with the same IV, so it's this chunk of random data that we use to initialize the cipher, and the same key on two or more distinct sets of input data shall be no greater than 2 to the minus 32. And in practice, this requirement is almost as important as the secrecy of the key. Wow, yeah, so that's important. It's a big deal. And it means that just blindly cloning is something that could break the security of this very fundamental, very widely used piece of cryptography. And it's, there are many, many similar requirements from that whole world of security, from the world of simulation, and even basic things is like issuing unique identifiers for database keys and so on. And so we need to fix this. What are the properties that we need that to have? We need to have a very high probability of success. This actually just has to work with very high probability every single time because it's so important. We can't sacrifice fast restore time. That's why we're in this game. That's why we're using snapshots. We can sacrifice snapshot time a little bit. And so there's interesting options there. We need this to be efficient. We need it to be simple. And so because of that compatibility, we need to get this accepted into a wide variety of libraries, of frameworks, of operating systems, and so on, right? We can't make this a proprietary AWS-only mechanism. We need it to be compatible with containers and sandboxing, and so it can't be based on things that a typical container or a typical sandbox doesn't have access to. It needs to have a widely available API. And then finally, it's something that libraries must be able to consume without app support. So if you get a new version of a cryptography library, it should be able to handle this use case without you changing your application code again, because of that compatibility requirement. And so we've proposed several fixes to this. The links down to where we've discussed this with the open source community are down in the bottom of the slides. The first of these is a new madvise flag called madvise wipe on suspend. And this is a flag that says, take these pages and after, before you take a snapshot, before you write down those snapshots, just zero them out. And this is an idea based on, something that AWS contributed to Linux a couple of years ago, which is a similar madvise flag called wipe on fork, which was aimed at solving a similar cloning problem related to fork and PRNGs. And with wipe on fork, you say, these pages should be the child contents are zeroed on fork, whereas wipe on suspend is going to wipe at kind of snapshot creation time. And it's also useful not only for solving this RNG problem, where the RNG should look and make sure, and as soon as it sees an empty page, it should re-init itself. But it also allows marking of sensitive areas like keys, which you might not want in the snapshot for whatever reason, and might want to reload from somewhere like an HSM on restore. And so it's quite a flexible, useful mechanism. The second fix that we proposed to the Linux kernel community is VmGenld. This is something that exists already. Multiple hypervisor vendors support this. It's supported by Microsoft. And this is a device, a file, or a VDSO operation that allows you to say, what is the current identifier of my virtual machine, and tell me if that changes. And that could be a blocking read, it could be a page that you poll on, it could be a page that you check, before issuing every random number generator, or any randomness from your random number generator. So it's a slightly less flexible mechanism than wipe on suspend is, because it doesn't do the secret hiding and so on. But it is also a mechanism that is supported elsewhere in the community. And we're sure there are others. And part of the reason that we want to talk to the larger systems community about these challenges is that we think that these are going to be common challenges in operating systems. We think that snapshots are going to be a basic building block going forward. And so we want to make sure that the whole community is thinking about it and is aware of the challenges here. And then I wanted to talk a little bit about networking, which is a related challenge. And so, we have the micro VM, and again, it's a micro virtual machine. It's got a kernel, in our case, a Linux, mini Linux guest kernel, and that kernel contains a whole lot of network state, right? State about the TCP connections it's opened, the TCP connections it's received, things like contract, and so on and so on. And so there's a whole lot of kind of network state, and that state needs to be kept sane to talk to a remote server. It also needs to be kept singular, because if you take this micro VM and you clone it, and now there are two that are trying to use this state, well, that's really just going to confuse the remote server, or it's going to break TCP, or it's going to have a bad impact. The best possible outcome here is probably broken connections. And so this is a real challenge too, right? Like, we want to have super fast restore. And part of super fast restore is having the connections back, so you can do real world work, because you want to go and talk to those remote services, to the DynamoDBs and the S3s and all of these other services, to your own microservices over the network, and that needs to come back quickly. And so there's been some really interesting work here around this, around fast reestablishment, quickly reestablishing TCP connections, TLS sessions, and so on. TLS 1.3 has some good work here that makes this easier, but there's more work required. There is work like there's an opportunity to use proxies and shims, kind of mid-level network layers that are clone aware, that know about that this is going to happen, and can help with things like connection pooling and so on. And then finally, there's an opportunity for protocol-aware session managers, like the Amazon RDS proxy. And this is something that knows the database protocol quite deeply, and can use its knowledge of a protocol to pool connections, to reuse connections, to clone connections, and so on. We're doing a whole lot of work here. We think there's a lot of interesting research work. We think there's a lot of interesting engineering work, but also interesting kind of bigger picture thinking about this problem of handling clones and super fast restore. And then the third challenge I wanted to talk about pretty quickly is cache freshness. And again, this is because we want to be compatible. We want people to be able to bring the code that they have already. And in a lot of cases, for programs written for a more traditional world, snapshot restore violates the kind of normal monotonic movement of time and violates temporal locality. And so there's kind of time travel aspect to snapshot, clone, and restore that code doesn't necessarily expect. And this is okay if apps are expecting it. It's actually, time is still monotonic, and so it's not that hard to deal with, but compatibility is a real challenge. And this is something that I think we're thinking about in the programming language space. We're thinking about with various runtimes and language virtual machines. But we think there again is really interesting research work and engineering work to be done in this idea around what does it mean to have a cache? What does it mean to have temporal and spatial locality in a world where snapshot and restore are very basic primitives used to build the compute platform? And so we're very excited to be working in that space. Well, thank you very much. I'm just extremely excited about virtualization, about operating systems at the moment. I think there is a massive amount of innovation going on, both in academia and industry, and very excited about being part of that conversation, and can't wait to read everybody's research papers. Thank you.